The science of climate change. In this section, we're going to discuss the science of climate change, and then we're going to discuss the implications of the results that we see on renewable energy, how that may or may not impact renewable energy. There's a lot of controversy. I would like to spend some time talking about the science and how we know that the Earth is warming. So first of all, we know because we've kept records, despite what it says here, for 150 years. We take temperatures in the land, the air above the surface of the ocean, and the air above and below the surface of the water. Rather, we take air temperature, land temperature, and water temperature. And here are three graphs of the last 160 years. This first one back here is the overall average temperature, global average temperature, with a 95% confidence range. Here is the land temperature, and here is the surface of the water temperature. And all of them we see a long period of time where, and notice this is a mean temperature here, an average, if you will, of 0, and this is above it and this is below it. And for most of the time we've been taking records until somewhere right in here, which would be somewhere around 1970, 75 at a guess. This range basically stayed completely or 99% below this average temperature, this 0 range. And then after that it rose, as we see, dramatically. This is a graph of temperature from 1970 through 2010. And this graph shows the difference off the 0 point, and it also shows from the first IPCC reports the range of scenarios that might occur, and based on the range of those scenarios, it also superimposes what actually happened. So this is what was predicted by models depending on which scenario you chose, and each of these black lines and blue lines are scenarios of what might happen depending on conditions, and the red is what is actually happening. So you could see that the red is right in the middle of the predictions of possibilities of what might happen that were made back in the 1990s. So what do we learn from these graphs? We learn that there was a fairly stable average temperature through the late 1800s. Up and down. There were some cycles, and we'll talk about that in a few minutes. Then it seemed to stabilize off in the 1900s, the last of the 1900s, right in this area. And then we see, starting somewhere after 1950, probably around 1960, a very sharp rise in temperature. Another way we know through direct observation that the Earth is warming are glaciers. This is a graph of the annual loss of the mass of glaciers. The red is the thickness, blue is gain, and there have been a couple of years obviously where it's gained, but the predominant has been loss of ice on the glaciers. And these are some pictures. The top is 1913, the bottom is 2005. This is the Shepherd Glacier in Glacier National Park in the United States. This is in Switzerland, and this here is a photograph from the 1950s, and this is a photograph from the 2000s. We also know through loss of polar ice. And this is ice falling off of Greenland, whole chunk of it. This is the size of Rhode Island, breaking off a couple of years ago. As the ice comes to the water, it shears off. Here's Greenland. This is the ice cover in 1992. This is the ice cover in 2002. This is a very interesting image. Now, this is not total ice cover. You must read this carefully. The Greenland ice sheet on July 8, 2013 on the left, and 4 days later to the right. In this image, the areas classified as probable melt are in light pink, correspond to those sites where at least one satellite detected surface melting. The areas classified as melt, dark pink, correspond to sites where 2 or 3 satellites detected surface melting. So the dark pink is all this area here, and here's the light pink in here. And this is over 4 days. 4 days difference in July 2013. Now, this does not mean that all of this, the ice melted. It means there's melting on the surface. Several satellites caught this, and one satellite caught this area. This is a decrease of the ice mass of the Greenland ice sheet from about 2000 to 2006. And you can see the ranges up and down the cycles. But when we take in and average out the ranges, this is the path. Less and less ice. These are the temperature records at Antarctica's Scout Base over the last 50 years, from the time that Shackleton first went to Antarctica to almost 2000. And what do we see? We see a rise of a few degrees average temperature. And this is, remember, they've got a different, their winter is opposite from ours. So April through November is the winter, and then this is the summer. This is the warm season. So far we've been talking about direct evidence that humans have collected using thermometers. Since thermometers were only invented 150 years ago, this could be rather limiting, and we need to find evidence that goes further back for what the Earth's climate was. This evidence is indirect, and it's sometimes called proxy evidence. Please don't mistake being indirect with being inaccurate. We believe that this is fairly accurate, and I'll show you as we discuss these how we get that feeling, why we get that feeling. So the first thing we can find out through proxy evidence is through tree rings. As you know, we can count back with tree rings, and we can see, for example, here we see areas where there was a lot of moisture and where it was drier. From tree rings, we can also find out the cloud cover and the amount of moisture and the temperature over a long period of time. Here is a temperature record from tree cores, and the pink is the pink is the tree rings, and the blue is the recorded temperature. And so for this period of time from 1850 through 1980 on this graph, we can see the relationship between the tree rings and the temperature. So using this, we can see that there's a correlation, and we can therefore make estimates going back further. And if we were to have the data on the trees from just before 2000 to present, presumably that pink line would follow the actual temperatures that we are recording. So we get good data going back 500 years from tree ring samples, but we'd like to know the temperature of the Earth before that. And there are ways for us to know that. One of them is through boreholes, which are holes in the Earth which have been drilled by humans. We know how much heat is coming off of the Earth, and we know how much heat is hitting the Earth, and we know the conductivity of the Earth. And therefore, we could tell what the temperature should be at any given depth. If the temperature is different, that's a reflection of the temperature difference in the atmosphere. And the further down that is, the longer time it's had to radiate. So the further down we go into a borehole, the further back in time we can tell what the temperature of the atmosphere was. And for the first 100+ years, we have data. And that data is reflected in the black squiggly lines that go up and down from about 1850 through 2000. And the black line that's surrounded by a blue shaded area is the temperature from these boreholes that we believe the Earth was, the atmosphere was at that point. And that temperature is reflected in this graph as a difference from today. In other words, when we go back 1,500 years, the temperature was about 1 degree cooler than it is today. Now, we could correlate the last 150 years with those black squiggly lines so that we know that we're getting an accurate measurement by looking at boreholes. As we go back past that, the black line you see going back is what we believe from the boreholes the temperature of the Earth's atmosphere was relative to today. And the blue shaded area is how much of how sure we are. And we're sure within that blue area. It's somewhere within that area. There's more unsurety as we go further back. Okay, how else can we measure temperature through proxy? Two important ways. One is pollen, and we can look at pollen and see what kind of plant it's from and the climate associated with that plant. And pollen is easily preserved in ice and in earth, and therefore we can see what pollen was where at what time. Because as we go back further, we, through a process called radioactive dating, can tell what how old some ice or some pollen is. So through direct measurement of temperature using thermometers, we've gone back 150 years, and through proxy measurements, we've gone back 2,000 years. This chart here is a chart of 10 different proxy studies which have been superimposed onto one graph. And what you see is they all follow the same pattern. This helps to validate the proxy study methods and also gives us a good firm idea of the global temperature going back 2,000 years. What's also interesting about this data is it includes one type of proxy measurement that we've not yet discussed. That's ice core sampling. Ice core sampling is taking cores from ice sheets from either Greenland or Antarctica, where they have been for very long periods of time. When a place is so cold that it never melts, and each year more snow falls than melts, a glacier builds up. And this glacier, over time, the pressure pushes down, turning snow into ice, and preserving it. Now, it's in the last 40 years, we've come along and started taking core samples and using methods such as radioactive dating. We can determine the temperature measurements, the temperature over time from these core samples. And we can determine them for long periods of time back into the past. In this case, from the Vostok ice core in Antarctica, we have a sample going back 400,000 years. And we can see the warm periods occurring on a regular basis and the ice ages occurring on a regular basis. And we can be relatively sure of this information because it's been trued with other studies, as we saw in the previous slide. But what's interesting about ice cores is they not only tell us information about the temperature of the atmosphere at the time the ice was laid down, but at the same time they leave bubbles, and those bubbles are samples of atmosphere from the same time period. So, for example, we have bubbles that are 400,000 years old, and we have samples of atmosphere all the way through this period. And here is a chart which shows both temperature and carbon dioxide that comes from those atmospheric samples in the ice cores. And look at what we find. We find a correlation. We find the temperature follows the CO2 concentration. As the CO2 concentration drops, the temperature follows. As it rises, the temperature follows. Now let's take a closer look at the carbon dioxide levels over the last 400,000 years. This says this graph here is over the last 650,000 years. And look where the high points are compared to our current level here. Put another way, this is in parts per million. And the highest it's been for the last 650,000 years is 300 parts per million. And here we are at, sorry, it keeps doing that, but where are we at here? 380, 390 parts per million. Way above historic levels. Here is a closer look at the carbon in our atmosphere, and what you see here are the seasonal changes from 1960 through 2010, showing the trend of more carbon in the atmosphere. Now, to understand a little more why this is important, we have to look at the Earth's energy balance. Because under normal circumstances, the same amount of energy that enters the Earth's atmosphere is returned to space. As we put more carbon into the atmosphere, this acts essentially like a blanket, although it's more complex than that, and it holds the heat in. What is the human influence on carbon in the atmosphere, and how do we know that the increases in the recorded carbon are caused by humans? Fossil fuel combustion results in about 7 gigatons per year of carbon being emitted into the atmosphere. We know this because we have a handle on how much is sold and burned. Also, another 2 gigatons of carbon are released due to deforestation. About half of all of this stays in the atmosphere, and the other half is taken up by natural processes. This is a small amount compared to the total carbon, but it stays in the atmosphere. And since it stays in the atmosphere, we've seen an increase in the carbon in the atmosphere from 560 gigatons in the pre-industrial era to around 800 gigatons today. That corresponds to an increase in a scale that's more familiar to us, and that is 280 parts per million carbon dioxide in pre-industrial times, up to that number we already saw previously, 390 parts per million. How do we know that this is due to human activity? Well, first off, we know because, as we already said, we have records of how much fossil fuel is sold and therefore how much is burned. Fossil carbon has been buried for hundreds of millions of years. Therefore, it's depleted in the radioactive isotope carbon-14. Furthermore, living things take up stable carbon-12 more readily than they do stable carbon-13, and living things are the origin of fossil fuels. Therefore, fossil carbon is also depleted in carbon-13. Examination of the isotope composition of atmospheric carbon today shows that it is becoming increasingly depleted in carbon-13 and carbon-14, indicating the fossil origin of the added carbon. Where does this lead us? The United Nations and the IPCC used computer modeling to follow 6 different scenarios into the future. And what they found were the 2 that limited carbon the most were the ones, obviously, that kept these numbers down. Now, many scientists have said that doubling the pre-industrial levels of carbon in the atmosphere from 280 to 560 is about all we can take, and above that we would suffer catastrophic damage to our environment. And the only 2 scenarios which keep that below are the black and purple, both of which involve a significant cut in carbon. Since most of the carbon that's adding to the atmosphere is from human actions, if we were to limit these actions, and the biggest limitation would be stopping burning fossil fuels for energy, if we were to limit carbon, we could keep, as you see by these scenarios, we could keep the amount of carbon in the atmosphere to just under double, or just about doubling, the pre-industrial amounts. All the other scenarios, including the red one, which is business as usual, which is where we are now, have us going up not only doubling, but almost doubling again. We come back to our familiar J-curve here. There's much more that could be said about the details of climate change science. What I've tried to do here is give you a basic overview of how we know what we know and how we come to the conclusion that we need to find other alternatives to fossil fuels for our energy, which leads us back to the theme of this class, which is it renewable energy's time now? Given the issues surrounding climate change, the adoption of renewable energy systems to replace fossil fuel burning energy systems seems like a logical progression. Thank you for listening.